Hello, my name is Mike Kolbeck, and today I'll be walking you through my implementation of Simacogo. So first, let's launch the program and see what it plays, how it plays. So first, it's going to ask what ply we want to play the game at, meaning how deep down the search tree do we want to investigate it from board positions. I'm going to enter 9 here, though it does support maybe up to 13 or 14 before it really stops working too well. Then I will enter the column I want to drop a tile into, and the AI player will automatically reply. Let's just play through a couple turns to see how it works. It's feeling kind of aggressive today. Go up to 5. We'll drop down to 7. Go 7 to try and block it there, and it will move up to 6. So the AI player, I've found, based on my implementations, pretty aggressive. Is able to both kind of point hunt pretty successfully while also blocking certain high-value moves that I try and make on higher plies. I'm not the best Simacogo player, but it seems to do pretty well and beats me a good number of times. So let's sort of peel back that and sort of investigate how this all works. So what we did here was we first started out in the Simacogo launcher, which contains the main method of the program. Now the way this works is it creates a new game, which is basically a wrapper for another object called a board, and then sort of alternates back and forth between asking first the player and then the AI what move they want to make. The human player just enters an input using standard in. The AI player, though, calls this opposing player.get next move, so the AI get next move, which we'll investigate in a second. So a game is essentially just a wrapper for another object called a board, just providing some input and output, though they do implement the same method, or the same interface. A board represents an individual board state and can be used either by the game object or a node board to represent the current game that's being played, or a hypothetical board state in the search tree. The way that this works is it contains a two-dimensional string array of 9 by 9 of different board pieces. As the game goes on, board is able to push new states to that board, and is also able to calculate the current score by make player move makes the plays. Score calls get adjacency points, which just iterates through the different elements in the board and returns their values. Node board works kind of similar, but it instead represents a game state, or sort of an imaginary game state of the intelligent agent. So how does the AI actually calculate any of this? Well, the way that it works is when the AI is created and get next move is called, it kind of creates an initial state of wherever the game currently is by getting information from the current game state. Then it calls minimax on it. The way that this works is it generates a tree of potential board states alternating between sort of the AI player and trying to find the highest value one, and children of the human player kind of toggling back and forth trying to find the highest value or lowest value nodes. When it bottoms, so the way that it works is any particular node sort of creates a list of all of its children, which is generated by the node board, which has a get all children function here. But it generates all the children, and then it checks through each one of them to see if it's sort of find the one that has the highest value, or if it's a human term, the lowest value. It does this by recursively calling minimax, the same function, on each one of those children, but passing it a lower depth, which would then bottoms out once the depth reaches 0, and that depth starts out being applied. So these nodes then percolate back up this tree, and they're checked against a persistent value, which is passed between the different calls to minimax. If they're higher, they're saved here in resulting node, and then returned. Same deal down here. Whatever came from a max node would then percolate up into a min node, and the lowest value one would be selected by the human player, or the expected human player's behavior, and returned until it reaches this sort of original call to minimax. Now, that produces an enormous search tree of 9 to the power of ply. So to deal with that, I've implemented alpha beta pruning. Really the way that works is that if you keep track in each call to minimax of a certain alpha and beta value, if, for instance, a node comes back with a value that's greater than the beta value or the maximum upper bound that the min node above it called, it just returns that node. There's really no point in finishing off this for loop and checking all of these and doing all of these recursive calls, because we already know that the min node above it isn't going to use it. So those all percolate back up. So the alpha and beta scores are sort of stored in the minimax calls rather than the node board, which more tracks the individual, like the game state and things like that. So once it has that, it returns the move that it wants to make back to the launcher, which then inputs that into the game state, and the game displays that onto the board. Thank you so much for watching. Bye.